we go. Section 3.2, graphs of functions. A lot of this will be repeat stuff that we talked about the past few. First off, domain and range. It says when trying to find the domain and range of a function by looking at a graph, imagine making a t-table for the graph. What values of x do we have corresponding y values? What values of y have corresponding x values? You could also imagine, and this is what we did last time, you could also imagine drawing a box around your graph. The left side up to the right side of the box would be your domain, the bottom up to the top would be your range. And we did work a problem like that a couple of chapters ago. Vertical line test. Talked about it a little bit yesterday's lesson, but if you want to use it, vertical line test is a way to determine if a graph's a function. If you can draw a vertical line and hit only one point on that graph, no matter where you draw that vertical line, that is a function. So let's try this one. Let's work example 1. Use the graph to find the following. First off, f of 1. And it seems like we've done this before also this year. Let me get my pen. To find f of 1, in just plain English, what that means is if you plug x into the function, or 1 into the function for x, what would you get for y? So you're going to go over to 1. There's where x is 1. That's where you're plugging it in. And then you go to wherever you need to go on the function. So notice you got an open circle up here. The function's not defined there since it is an open circle. So over to 1 and you'd go down to here. So at f of 1, what does y equal? Negative 1. Think about that before we go on any further. No matter what x you plugged in, do you ever get two different y's? Like there, you thought we might because you've got above and below, but we got an open circle there. 2, you've got one value. 3, you've got one value. 4, you got one value. That is going to be a function, which I know I'm getting ahead of myself, but for each x you have only one y. F of 0. Here's 0. That is going to be about 2.5. So when you plug in 0 for x, you go up, it's about 2.5. Negative 2, negative 1, negative 2 would be also negative 2. The domain. This is what I was talking about in that previous example. Where do your x's start? Where do they end? Well, you can draw a line. Your x's are your left and right. They start. Your graph starts there, and it goes to there. Does that make sense? So if I ask you what your domain is, domain is equal to, and let's do it with interval notation just for extra practice. Negative 2, including negative 2, up to 6. Do we include 6? Yes. Domain is all the things from negative 2 to 6. Any questions? The range. The range starts, your y values start here, and they go to here. So what would that be? Negative 2 to 3, and notice we're not including 3 because if you look, there's an open circle there, so it's going to go up to 3, but it's not going to include 3. That's what I was talking about, drawing a box around it. From left to right, your domain. From the bottom to top is your range. All the values are inside that box because it's got an open circle there. It goes up to 3, but it doesn't include that 3. Okay. Is it a function? Yes. Vertical line test, no matter where you draw a vertical line, this would be the only one in question. Is that vertical line, but that still only hits 1 point because the top one's not included. But vertical line, anywhere you draw it, you only hit 1 point. That is a function, yes. Analyzing graphs. It says a function is said to be increasing if it goes from uphill to left to right. Okay? If you're traveling from left to right, and you read it just like I'm reading these paragraphs. Anytime you read a graph, you read it from left to right. It's said to be increasing if it's going uphill, or if it has a positive slope. It's decreasing if it's going downhill. If the function is neither increasing nor decreasing, it's constant. And that would be your horizontal line. Any peak is called a local maximum, or plural maxima. Any valley is called a local minimum, or plural, that's a minima. We'll talk about all these with the next problems. Parts of the graph that are cupped up are called concave up. Let's look at this graph here. This part would be concave up, it holds water. This part would be concave down, it's cupped down. The point where it changes concavity, which would be somewhere right along in here. Yeah, the point where it changes concavity is known as its inflection point. All that's just vocabulary. Okay, example 2 says analyze the following graph. We're going to do this one with a graphing calculator. You can do it by hand if you wanted to, do your t-table and graph it. That's what we're going to do in the next 3 examples. Analyze the following graph. We're graphing negative x to the third minus 8x squared plus 8x plus 5. And we graph. And we see that we're zoomed way in on this. Okay, x to the third stuff will always look, well, most of the time look like you've got the down, up, down. Okay, you got 2 turns. Turns to the up and then turns back down. I'm going to change my window to try to get, because it's coming down, then going back up, let's try to get that bottom there in it also. We're going to have to change our y minimum. Let's try negative 20. See if that gets it. Still doesn't get it. Let's try negative 40 maybe. Let's do negative 30 first, just to test. Still didn't get it. Yeah, I'm going to have to change my scale, definitely. I'm going to try negative 50. I think I can get it with negative 50. And the scale, let's do 10. God, still ain't there. We'll try negative 100. Scale, I think 10 will still be fine there. Still ain't there.
Almost. Yeah.
Negative 120. There we go. So you see here the graph of this. To where let's talk about when it says analyze it. You got to tell me what the maximums, the minimums are. You could tell me the intercepts if it asks for it. Your x-intercepts, your peaks and valleys. You got a peak here, you got a valley here. Where it's decreasing, you remember a while ago when I was talking about decreasing, increasing. Inflection points, I don't think you have to give. Because some calculators will do inflection points for you. I don't think this one will. But let's talk about first off increasing and decreasing. From left to right, you're always reading your graphs from left to right, just like a book. We're decreasing, going down, until we hit that minimum point. Then we're increasing from that minimum point to the peak here, and then we start decreasing again. Those are going to be the intervals where we're increasing and decreasing. So before we do anything else, the best thing to do is to find these peaks and valleys. The menu that you use probably more than any other whenever you're talking about graphs is that second calc. Minimum, maximum. That's what you're going to do. Your minimum, let's find it first. Minimum. So we're looking for this minimum here. Do you see it's going to be somewhere between, I think, did I do negative 10 to 10 on my x? I don't think I changed it. So it's somewhere between negative 10 and 0. A guess, just get close to it. Don't really even have to be close to it. You see, there's your minimum value. Negative, can't hardly read it. Negative 5.8, and that dot's blinking right there in the middle of it. That's the reason you can't see. So negative 5.8, we'll call it negative 5.9, rounded up, negative 115.4. Negative 5.9, negative 115.4. That was the minimum value. Now let's do the exact same thing and find your maximum. So second calc, maximum would be 4. We know it's between 0, well, let's say negative 2 and 2, somewhere in that neighborhood. Guess, just hit enter again, it'll find it. So 0.46, or we'll call it 0.5, 6.9. That's your max. So your minimum here, maximum here. Now let's talk about where is it increasing, where is it decreasing. This is what you'll put. Your graph starts out decreasing, and we'll use our interval notation. It's going to be a whole lot easier. It decreases from wherever out here down to this point. And we're moving left to right, so we're going to use our x's to describe it. It decreases, I'll do the first one for you, from negative infinity to this minimum point, which would be negative 5.9. Any questions on that? Not including those points. It's not actually decreasing at that point. It stops there. And then it starts increasing. You tell me that. Tell me where it increases from and where it stops at. To 0.5. Use your x's. This is, don't get, that's the only time you might get it confused. These are x, y's. These are your intervals. That makes sense. You're talking about a point here. Here you're talking intervals. And then it starts decreasing again. And it decreases from to positive infinity. That's all you got to put. There's your intervals for decreasing and increasing. I don't think you have to describe where it's concave up and concave down, but I do want to talk about it. Your concavity is up from here to here. Do you notice it's up there, and then over here it's down, but where does it change at? That's the problem. With this being kind of symmetric the way it is, or it's having rotational symmetry, the concavity for this one will be directly in between the minimum and maximum point. Does that make sense? Somewhere right in there. So you could actually average, in this problem, you can look at the graph most of the time and tell. You could average your x's there and tell where it's going to be, where it's going to change concavity. But some of the problems might ask you, where does concavity change or whatever. In this problem, let's see, that's negative 5.4, negative 2.7. Negative 2.7 something. I'd have to check my y value there, is where it's going to change concavity. So it'd be concave up from negative infinity to negative 2.7. It'd be concave down from negative 2.7 to positive infinity. Any questions? Here we go. The next problem says graph the following functions. The way I want you to graph these is by using graph paper. Okay. On these problems, they're simple graphs. I don't want you to do it on. You can check it on graphing calculator, but I don't want you to do it completely on graphing calculator. First one says y, or f of x, equals the absolute value of x squared minus 3x minus 2. To graph this, we're going to do a t-table. Let me tell you the easy way to do a t-table. I'm not sharing with you how to cheat, but this is what I would do. Even though I told you not to use your graph calculator to graph it, you can use it to make your t-table. This comes in handy. Once you get to college, watch closely, and this will get you around having to ever make a t-table again. Because if I actually want to make a t-table, I'd have to pick values, let's say negative 5, and we'd plug it in. And we'd say, okay, negative 5 squared, negative 3 times negative 5 minus 2, that'd be 25, plus 15 is 40, minus 2 is 38. The absolute value of that is 38. And we'd have to go down through there and do that for each x value. Here's how to do it. Typing in the absolute value of that stuff, here's where you find that. Under catalog, did I show you that the other day? ABS. Y equals the absolute value of x squared minus 3x minus 2, close. Remember what I told you that would look like? What's the absolute value do to stuff? It makes it positive. Normally that graph's a parabola. Normally it looks like that, but what if part of it's below the x-axis? It's going to flip it up. And you're going to see when I hit graph, that's what it's going to look like, well, when I change my window. Window, well, zoom, standard. There you go. It's a parabola with the bottom part of it flipped up above the x-axis because it's absolute value. Made it positive. But how do you do a table? Right here. There's your t-table. Second graph does your table for you. Never have to do another table again. If you want to change, if you wanted like 0.5 and all that, you can go to table set, which is above window. You can do second table set, and you can say, okay, where do I want my table to start? Triangle table. What did that triangle mean? Second table set. That is delta. Delta is the change in. The change in the table, 1. If you wanted it to go up by a half, you could put a 0.5 there. Independent and dependent variables, if you put independent ask, you can actually plug in the values you want to plug in. Look, let's go down to that and I'll show you what I mean. Put it on ask and then go back to your table, it's blank. If I wanted to plug in negative 4, then I can put negative 4, hit enter, and it plugs it in for you, 26. Makes sense? But I want negative 3, negative 2, negative 1, 0, 1, 2, 3, 4 since I'm out of room. Shouldn't. Negative 4 and 4 might, but I don't think it's going to because it's not. But again, since I want these values, I'm going to go back and just change it back, and I can go. You can scroll up and down your table. So negative 5, 38, negative 4, 26, negative 3, 16. Let's actually take and graph those up. This is what you'll do on your homework. Just put your crosshair for 0, 0. You got negative 5, 38 is not going to fit. Let's start at negative 3, 16. So go to negative 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Negative 3, 16, negative 2, 8, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, and 0, 2. One, 4. And you just continue on and on. Does that make sense? You'll put more of them on there. Here's the thing though, if you don't get a good enough graph, and I'm not going to finish this graph out, but if you don't get a good enough graph, if you need more points, you can go back and change it to, okay, what about when x is negative 0.5 and you get you a point there? I think that's actually 0. Connect your dots. It does look like, should look like this. Comes down, it's going to jump back up, and then it's going to go back up again. I'm not going to complete it, but you get the idea. You see how to actually graph that. Okay, on the second graph, we got y equals 2 times the greatest function, greatest integer function. Floor function is what I like to call it, and that's what I'm going to call it most of the time. 2 times the floor function of x minus 4. And Brittany, that kind of answers your question from yesterday. Will you ever have anything in there with it? Yeah. On your table here, and if you can do these tables in your head, great. It'll save you a lot of work. Think about things that you can plug in. When you plug in 1, when you plug in 2, when you plug in 3, it doesn't give you the full graph, because if you just plug in whole numbers, it's going to make it look like it's a line, and it's not. Let me go through and let's plug some in. When you plug in, let's start with 0. 0 minus floor, this is the rounding down function. 0 minus 4 is negative 4. It's already rounded. 2 times negative 4 is negative 8. So 0, negative 8. 1, 2, 3, 4, 5, 6, 7. It doesn't really fit. I'll just put a dot down there. When you plug in 3, or let's do 1. 1 minus 4 is negative 3. Round down, it's already rounded. 2 times negative 3 is negative 6. 1, 2, 3, 4, 5, 6. And if you just do that, do you see it's going to look like it's a straight line? But it's definitely not. What you're going to have to do is plug in the stuff in between them. Plug in 0.5, plug in 2.5, plug in 3.5. Let's start with, just so you can get an idea, and it's easy to subtract, plug in 4.5. 4.5 minus 4, what is it? 0.5, but this is the rounding down function, so it's going to round down to 0. When you multiply it by 2, you get 0. So when you plugged in 4.5, you got 0. So 1, 2, 3, 4.5, you got 0 as well. If you plug in 4.6, 4.6 minus 4 will give you 0.6, which also rounds down to 0. 2 times 0 is 0. And what's going to happen if you plug in anything between 4 and 5, it always get 0. So this is actually what this looks like. And I wished I'd have changed my scale a little bit. Anything from 4 to 5, you're going to get 0. Put an open circle there, because once you plug in 5, it jumps up here. Anything you plug in from 5 to 6, you'll get 2. Put an open circle. Anything you plug in from 6 to 7, you'll get, well, I said 2. You'll get anything between 6 and 7, you'll get 4. Anything between 7 and 8, you'll get 6. And this is actually called a step function. I don't know. We'll try it. I don't even know what the function is on a graphic calculator, but it looks like steps, because anything between there and there, it's going to round down and give you that. So you've got these open circles. Is that a function? Yes, it is, because you've got open circles at the end. If you draw a line straight down through it, you hit a point here, but you don't hit a point here. That is, if you draw a vertical line test, that is going to be a function. We'll try to find later on, we'll try to find that function on your calculator. The last one of these we're graphing by hand is a piecewise function. Need to know how to graph piecewise by hand. Negative 2x minus 2. it says if x is less than -3, I'd rather write that if you go from -infinity to -3, not including -3. X minus the floor function of x if we're between -3 and 1, including both. And 2x squared if we're from 1 to infinity. This is going to be a pretty ugly graph. It's just not really hard, but it's just time consuming. Let's try it. You can make a table for each piece. The first one we're plugging in stuff from -infinity to -3. So plug in -2. What do you get? -2 times -2 minus 2, 2. So -2, +2. Plug in, well, what was wrong with that? Thank you. Thank you very much. You can't plug in -2. I was testing you. -4 instead. That would be 8 minus 2, which is 6. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. You can plug in -5, you'll get 10 minus 2, which is 8. And you see the pattern there. That would be linear. The first one's linear. You can plug in everything up to -3. Here's where it gets a little bit, hopefully not confusing. I'm going to plug in -3. Because you can plug in everything up to that, but it does not include it. So I'm going to plug it in, but I'm going to put an open circle there. Because our graph goes up to that point and it stops there. So plugging in -3, you get, what? 4. And that is going to be an open circle. -1, 2, 3, 1, 2, 3, 4. Open circle. There's the first part of your graph. And it does go to -infinity, so put you an arrow. It keeps going in that direction. The second part of your graph, you can do a different t-table for it. Erase your first t-table or do a separate graph, x, y. And you just do plug in stuff from -3 to 1. When you plug in, and it does include -3 there, when you plug in -3, you've got -3 minus the floor function of -3, which is actually, round down, you still at -3, that's going to be 0, right? Let me change, I'll change colors for the second part. It's going to. If you plug in yeah, I was right. -2.5. That's between -3 and 1. Plug in -2.5, you get -2.5 minus, round down -2.5, down, -3. So that's -2.5 minus a -3 would be -2.5 plus 3, which is 0.5. So when you plugged in -2.5, I put that blue in the wrong spot, didn't I? Y'all gonna have to catch me today. I'm off. Just where it's two different graphs. I had to erase that blue dot. I put it in the wrong spot. Y'all watch me close. I'm making all sorts of mistakes today. So that's 0.5. -2.5, we're at 0.5. If you plug in -2.4, what actually happens here is it's still a step function. It's going to go up to here, and you're going to have an open circle there. And then let's plug in from -1 to -2. Just plug in more values. I'm skipping just to save time as far as so you get on your homework. When you plug in -1, I don't even know if you'll have a piecewise or not. You will have a piecewise. I don't know if you'll have one of these greatest integers. You've got -1 minus, round down -1 is still -1. So that goes back to 0. So at -1 you're at 0. If you plug in -0.5, you get -0.5 minus, if you round it down, you get -1. That's -0.5 plus 1, which is 0.5. You see what happens? It does the exact same thing. And this one is too. And we're graphing that up to from -3 to +1. So we're going to there. Is that a function? Is that part of it a function? Sure. Vertical line hits only one point. Here, even though that's an open circle, you're still just hitting one point. That was the hardest part of this graph. The next part's easy. The last part, I'm changing colors again. We're going to graph now 2x squared from 1 to positive infinity. Let's plug in 1, 2, and 3. Plug in 1 into 2x squared, what do you get? 2. Plug in 2, what do you get? 8. Plug in 3, what do you get? 18. Plug in 1, we got 2. Plug in 2, you got 8. 1, 2, 3, 4, 5, 6, 7, 8. Plug in 3, you get 18, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's 1 is not included. Yep, I should have included it here, shouldn't I? So that's going to be a dot there. So you got an open circle at 1, 2. And that's, I know you can't tell, but that's actually a parabola. And as ugly as that thing is, you've got three different, the biggest thing to know, you've got 3 parts. The black is the first part, the blue is the second part, the red is the third part. That is a function. As ugly as it looks, it is a function because it just jumps. And you notice you got an open circle up here and a closed one down here. It's still vertical line test only hits 1 point. That is still a function. Okay, the very last part says graphing parametric equations. This is a little bit more important. It's important that you know how to do the piecewise functions, but parametric equations, watch. Especially anybody that has to take any physics-based stuff, you're going to do a ton of parametric equations. In a parametric equation, the independent and dependent variables, your x and y, are defined in terms of a third variable called a parameter. Most of the time, this third variable is t and stands for time. The equation then tells you a horizontal location and a vertical location after a specific time. A table of values can be used to graph these equations. However, a third column must be added, and values of t are chosen to plug into the 2 equations. Let me explain what I'm talking about. It's going to give you an x and a y. X equals 3t minus 2. Y equals t squared plus 4. But the thing about it is, your x and y, it's not going to be like y equals 2x plus 3 anymore. Your x and y are going to be defined in terms of some other variable, like I said, normally t or time. What you're going to do is you're going to plug in different times. After maybe plugging in 0 for t, it's going to tell you where's your x and y after 0 seconds or minutes or whatever it is. When you plug in 1 for t, it's going to say where's x after 1 minute and where's y after 1 minute. After 2 minutes, where's x after 2 minutes and y after 2 minutes. So it tells you more about your equation. You've got some sort of motion involved. This object, whatever it is moving along your curve, and at any certain time you can tell where it's at. For this problem, it also tells you this: -3 is less than or equal to t is less than or equal to 3. It tells you what to plug in for t. A lot of your problems will do that. So as you're doing these problems, you're going to do it the same way. You're going to have x and y, but you're going to add a third column, which is t, and that's what you're plugging in for your t's, so you can find out what x and y is. These are really easy if you watch. We're plugging in from -3 to 3, so -3, -2, -1, 0, 1, 2, and 3 is what you're plugging in. And you simply take the x, plug all those in. Take the y, plug all those in, and you've got your points there, your x and y's. And then you just plot those points. So it's the same thing, you've just got kind of one extra step. Take each of them and plug in -3. X equals 3t minus 2, plug in -3 is what? Careful. -9 minus 2. Be -11. I tell you what, let's go down and just plug all of our t's into the first one first. Plug in -2, you get -6 minus 2, which is, plug in -1, -5. Do you see the pattern? -11, -8, -5, and you can do that. You should have a pattern after a while. So there's all your x values. And then you do the exact same thing for your y's. Plug in from -3 to 3 into your y equation. Plug in -3, you get 9 plus 4, 13. Plug in 2, you get, plug in 1, or -1, 5. Plug in 0, plug in 1, 5, 8, 13. And then you simply plot those points. -11, 13, -8, 8, -5, 5. So let's do this in XY axis. Your first point, negative 11, 13. That ain't going to fit. Let's scoot it over. Negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Negative 11, 13, negative 8, 8. 1, 2, 3, 4, 5, 6, 7, 8. Negative 5, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. What shape do you think it's going to be? Negative 2, 4. That's right. 1, 2. Negative 2, 1, 2, 3, 4. It is going to be a parabola. But your parametric equation is actually a line and a parabola if you look back. 1, 5. 1, 1, 2, 3, 4, 5. And you can see it's curving back up now. 4, 8. 2, 3, 4. 6, 7, 8. And if you actually just count over, you could find where your other point's going to be, but 7, 13, 1, 2, 3, 4, 5, 6, 7, 13. Something I do need you to watch on this. Do I put arrows on both ends? No. Because we're only graphing from t equals negative 3 to t equals positive 3. So, why do I connect my dots though? Why does it include the stuff in between? You're not just doing negative 3, negative 2, negative 1. It's all the things between negative 3 and 3 is what you're graphing. So it's all the stuff between negative 3 and 3. And you do, there you go, there's another good one. If that was just less thans, you'd put open circles on the ends. Let's see, you could go back and label this. This is t equals negative 3, this is t equals negative 2, this is t equals negative 1. So you can see the progress. As some objects traveling, t is negative 3. Most of the time you're going from t equals 0 to something, but in this case t is negative 3, travels along this, and at t equals positive 3 you end up over here.